This is the third and last video talking about structures of linear systems. Of course, that's not the end of linear algebra. We still have a lot ahead. Like we still have at least 12 of so videos after this one. Or I mean, or even more than that, like that, maybe like 16 videos after this, most likely. Right. So, but this is the last under systems, I mean, structures of linear systems. We've been talking about things like rank and all that. In this video, I'm talking about rank nullity theorem, which we had considered previously, like in the video talking about null space, column space and null space. We had talked about rank nullity theorem. So we want to see it in a more breadth here, in more depth in this case. Okay, let's go ahead and talk about the rank nullity theorem. Okay, let's start with this. Let T map V to W. All right, this is the statement of the theorem now. Let T map V to W be a linear transformation between finite dimensional vector spaces. Then we say that the dimension of V, the dimension of this V now, is actually equal to the rank of T plus the nullity of T. The rank of T plus the nullity of T. In the last video, we already saw what rank is about. Rank is simply the number of non-zero rows in a matrix after you have reduced it to either row echelon or reduced row echelon forms. So where rank of T, of course, is the dimension of the image of T, nullity of T is the dimension of the kernel of T. Now, all of these are related to null and all these things. Then dimension V is the dimension of the domain itself. Like that's the overall domain. Now let's look at it. So if A is an m by n matrix, then you say that the rank of A plus the nullity of A is equal to, m by n is number of rows, while m is number of rows, n is number of columns. So the rank of a matrix A plus the nullity of a matrix A is equal to the number of columns of the matrix. So where n is the number of columns, the rank is the number of pivot columns, right? So, this the other time when we looked at rank, we saw it as the number of non-zero rows in a reduced echelon form of a matrix or reduced row echelon form of a matrix. The nullity is the number of free variables. So again, we still talk about the whole idea of echelon form, right? And then you count the pivot variables, the pivot columns, the columns that have pivots. That the number of pivot columns you have is the rank. The number of free variables you have is the nullity in that case. Okay, so let's see the idea of kernel. Kernel is null space. We saw null space the other time, except that we are looking at it not in that context. So the kernel of T is this. Kernel of T is the collection of all V in that V. That V is the input set, if you like, all right, that is mapped to W. So the kernel of T is V belonging to V such that T of V is 0. So it's the same thing as kernel where we said AX is equal to 0 instead of AX being equal to B. So it contains all vectors that map to 0. So the kernel contains all vectors that map to 0. So the nullity of T then would be this, that the nullity of T is equal to the dimension of the kernel of T. All right. So the nullity talks about, just like we know, it talks about the number of zero rows. That's the nullity now, right? So, but rank is the number of non-zero rows. So number of non-zero rows plus number of zero rows. Or in this case, we are talking about columns actually. So that gives us the total of columns in that situation. So for image now, the image talks about the range. So the image of T now is the collection of all T of V such that V belongs to V. So it contains all outputs of T. So in this case, the rank of T is actually the dimension of the image of T. Okay. So let's look at the intuition behind rank nullity. So every vector in the domain does one of two things. It maps to 0. That's the kernel. So every vector that maps to 0 is the kernel. Then it produces a new direction. So every vector that produces a new direction is image. Now, the idea of producing a new direction means that, if you have if you have a vector like 1, 2, 3, and you have a vector 2, 4, 6, the vector 2, 4, 6 is not producing any direction because it's simply a multiple of the 1, 2, 3 vector, which we already have. So 2, 4, 6 is not adding any new information like we've been saying. So the domain then splits as this, that V is the kernel part plus the image part, so that the input space is equal to the lost directions, that is those ones that are mapped to zero, the kernel, and the useful directions, those ones that produce new direction. So we have a machine analogy. So think of T as a machine. So some inputs are destroyed, that's the kernel. Some inputs produce outputs, that's the rank. So total output will be the destroyed plus the useful ones, like that. So, and we have the geometric interpretation also, that if T maps a three-dimensional system to a two-dimensional system, one direction collapses into zero, that's the kernel. Two directions remain, and that gives the image. So in that case, we say 3 is equal to 1 plus 2. 1 for the zero or the kernel, and 2 for the remaining, which talks about the image. So, and then the importance of rank nullity is that, the property for 1 to 1, nullity is equal to 0. For onto, rank is the dimension of W, and for invertible, the rank of the dimension of V, the rank, of course, will have to be the dimension of V, so that nullity is 0. So for a matrix to be invertible, the rank has to be equal to the number of columns it has. Okay, so we have a guided proof here. So here things are a bit more abstract and technical and more technical than just solving for matrices. So if you want some proof kind of thing here, so it's the rank nullity thing is more or less like the things we've been talking about, except that this one is a bit more rigorous. So for guided proof, we want to prove that the dimension of V is equal to the rank of T plus the nullity of T. So step by step now. Step one, we talk about the basis of the kernel. So let the kernel of T span K1, K2 up to KR. Then we say R is equal to the nullity of T, right? R is the nullity of T, is equal to the nullity of T. So the set K1 up to KR is a basis of that kernel. Then for step two, we say that we extend to basis of V now. So extend the kernel basis to basis of V. So you already have K1 up to KR, and then you want to extend to the basis of V, which will now be V1, V2, all the way to VS. Then we know that the dimension of V is the nullity, plus this one now. So the dimension of V now is R plus S in that case. Then we can then apply the transformation. Like we can apply the T that is mapping V to W. So you apply T. So applying T now, we have T of Ki. All right, T of Ki, see all the K1 to Ki now. So T of Ki is equal to 0. T of Vj, on the other hand, is not equal to 0. T of Ki is equal to 0 because they are kernels, right? And kernels are those inputs that are mapped to 0. So that's why T of Ki is 0, but T of Vj is not equal to 0. So the images are, so for T of Ki now we have from 0 to R, we have R zeros. And for the VIs, we have T into, okay, for the VJs rather, we have T V1 all the way to T VS. And when all of that is done, we can talk about the spanning. So let Y be equal to T of X. We can then write that X is summation AI sub KI plus summation BJ for plus BJ VJ. So we then apply T. So T of X in all will just be summation, because all of this will go to 0. So it's just the summation of all the B sub J's, T of VJs, so that TV1 all the way to TVS will span the whole image. So in step 4, then we talk about independence. So we suppose that the summation of C sub J, T of Vj is equal to 0. Then we say T of summation of Cj Vj is equal to 0. So because T now can come out, and then we, by linear independence, we say that summation of Cj Vj belongs to the kernel of T. So we then say, by linear independence again, we say that Cj is equal to 0. Hence, the vectors are all independent. That's what we wanted to show. And in conclusion, we can say that the collection of all of T1, V1, T of V1, T of V2, all the way to T of Vs is a basis of the image of T, so that the rank of T is equal to S. And then since we recall that the dimension of V is R plus S, thus we can say that the dimension of V is now R. R is the nullity of T and the rank plus the rank of T. So S is the rank of T, like we found now. So the dimension of V actually is nullity of T plus the rank of T. So we can take an example. I mean, we've told a lot of stories. So let's bring the idea home by using matrices that we're familiar with, like that. So let 1, 2, 3, 2, 4, 6, 1, 1, 1 be a matrix. If you do row reduction, of course, we already know this is a multiple of this now. So if we do all that, we are going to have a matrix two row, I mean, a zero row here is here, and we have two non-zero rows, and then the rank is two. Then, of course, and we know we have three columns, right? So it means that the nullity is one, right? If the rank is two, the nullity is one because the addition of everything has got to be three. So if you check two plus one is three, like that. So nullity plus rank. So in essence, after you take out the rank, whatever is left is the nullity. So for a full rank matrix, it means that the nullity is zero because there's no nullity in a full rank matrix because all the columns correspond to ranks. So we have another example talking about linear transformation. So imagine this now. If you let t be x comma y comma z, which is equal to x plus t of x y z rather be equal to x plus y comma y plus z. So in domain R3, because we have x, y, z, right? So you can then solve. If you say x plus y is 0 and y plus z is 0, then we can say that, of course, we can express everything in terms of y because we have y out here. Of course, we can also choose other ways, but once we express, if you express x as a in terms of y, so x is equal to minus y and z is equal to minus y also. So what do we have for x, y, z now? So the coefficient of y for x is going to be minus one. For y is y, so the coefficient of y is one. For z, y is also equal to minus z, right? I mean, for z is equal to minus y, so the coefficient of z in that case is also minus one. So in that case now, you have minus one, one, minus one. And then, of course, the original matrix is this. So for row one, we have the coefficient of x is 1, the coefficient of y is 1. For z, for the first one, that's 0. For this one, the coefficient of x is 0, the coefficient of y is 1, the coefficient of z is 1. So that's the matrix. So in that case now, we know that we see that the rank is 2. If you do row reduction, we get a rank of 2. So by the time you check, you see that we have 1 plus 2, and that is equal to 3, So the nullity, so this gives us one nullity right here, and the matrix itself is 110 and then 011. So the rank is 2, the nullity is 1. So everything is three-dimensional because we are in 3D form, right? So this one clearly gives you a nullity, right? While this one gives you the original matrix itself, which has a rank of 2. Because I mean, if you want to do a reduction, just do zero. Okay, we want this to be zero now, and this is the pivot. Okay, this is already a pivot. Yeah, this is what we have already because this is already in echelon form, right? So this is a two ranked matrix. So then we have differential operator. Let's talk about differential operator in terms of rank nullity. So imagine this that T maps P3 to P2. Of course, we are talking about polynomials now because differential operator has to work on polynomials for sure. So T maps a 3-degree polynomial to a 2-degree polynomial. So the transformation of f, the T of f is f prime. So and the dimension of P3 is 4. The dimension of P3 is 4 in the sense that you have the constant, you have power x, I mean x raised power 1, x raised power 2, x raised power 3. So that's why the dimension is 4 like that. So in this case, the kernel is going to be such that f prime, f prime is 0. So f prime is 0 implies that f is constant, right? So in that case now, that's the only case where f prime is constant. So in that case, you have a nullity of 1. Okay. So and then since for image equals P2 now because you have taken out this one. So the image is P2. So the dimension of P2 now can then be 3. The image of P2 is here for P2 you have constant, you have x raised power 1, you have x raised power 2. That's why the dimension of P2 is 3 because of the constant, the x raised power 1 and x raised power 2. So the dimension is 3. So in that case now, you can, and again for this one, it means that here the rank is 3. So then we can, if we check now, you see that the nullity is 1 and the rank is 3, and 1 plus 3 is equal to 4. Talking in terms of differential operator like that. So, in summary, we can say the following that if the rank talks about the dimension of the image, all right, and the nullity is the dimension of kernel, the theorem we have the rank nullity theorem then tells us that the dimension of V, the dimension of maybe a matrix or so actually is equal to rank plus nullity. So the key idea is domain splits into kernel and image. of course. Then that's lost directions plus useful directions. Then this works for all finite linear maps and fundamental for solving systems. So it's just like what we did in the last video, except that this one is a bit more theory heavy. Okay. So practice problems now. Let's team up R3 to R to be defined by what we have here. Find the rank and nullity of T. Okay, just like what we did. Okay, I may have to do this to actually drive the point home. Yeah, I guess I need to do this. X plus 2y plus z, then y plus z. Okay. We want to find the rank and nullity of T. X plus 2y plus z, then y plus z. So we have T of x, y, z equals x plus 2y plus z, then y plus z, right? I guess that's what that is. Okay. So, and we're looking for, find the rank and nullity of T. Okay. So to find the rank and nullity, given this, to find the rank, find the rank and nullity of T, what do we do? First, we have so we start with nullity. For nullity, we solve the system. We have x plus 2y plus z equals 0. And then what else do we have? We have y plus z equals 0. Well, from here, um, what can we do? What can we do? If we want to solve this for 0. Um, Clearly, we're going to have multiple. We have yeah, we have 3 here, right? Trying to see what we need to do. So we need to solve this. Okay. What if I say this is equation 1 and this is equation 2? Maybe we can get some insight. Okay. So we can say let y be equal to minus z. So if y is minus z, uh, so from one we can then have x plus 2, or let's say z is minus y, right? This is also true for me. Z is minus y. So we have x plus 2y minus y, because z is minus 1, that's equal to 0. So we then have x plus y, 2y minus y, x plus y equals 0. So what else can we do? It doesn't help so much, right? Um, So we have written z in terms of y. So in this case now, this one only reduces to x plus y equals 0. So again, we can say that x is equal to minus y. That's all we can have there. So this now gives us the system we need, because there's nothing else we can do. So we can then have that x, y, z. So x is in terms of y. So we have y out here. So for x now, for x, we have minus 1. Y remains y, so the coefficient of y is 1. And then for z, we also have minus 1. So we have minus 1, y. Well, minus 1, 1, minus 1. Okay? Minus 1. So based on what we have here and here now. So, or better still, maybe I should just write it out for clarity's sake, in case that's sort of confusing. So here now we have let me go black. So of course we have x to be minus y, we have y to be y, and we also have z to be minus y. Okay, that's what I'm trying to talk about. So now we can have say x, y, z is simply like so for x we have minus y, for y we have y, right? For z we have minus y. So what we are just doing is to say y can come out. So we have minus 1, 1, minus y, minus 1. So here we just have for nullity now. Nullity, that was our solution for minus 1. I mean, for the system equals 0. So nullity is 1 in that case now. So now the next thing is we now form the matrix. We have T equals x plus 2y plus z, right? So from the original thing, t of x plus y, x comma y comma z. We have x plus 2y plus z, and then we have x plus y, I believe, from the original expression. Yeah, here, y plus z, right? Did I say x plus y? So it's y plus z. So we have y plus z, like this, y plus z. So we can form matrix. So we form the matrix corresponding to that, right? And we want to look at the rank of that matrix. So we have, um, so for x, so for x, we have 1, y2, z1. Then this now, x is 0, y is 1, z is also 1. So this is already in echelon form because below the principal diagonal, we already have 0. So the rank is equal to 2. So the rank is equal to 2. So what are we told to find, right? We're told to find the rank and nullity. So we can then conclude, so rank is equal to 2 and nullity is equal to 1, basically. Nullity is equal to 1. The whole dimension is 2 plus 1, 3, and it's correct with the dimension, right? So it's more like we're now saying the dimension of R3 now is equal to rank plus nullity. So the rank is 2, the nullity is 1. So the dimension is really in order like that. Okay, so I think that helps with that. So equation 2, let this find the rank and nullity. Of course, I can already see a multiple, so you want to check that out. Problem 3, let T be R4 to R3 be a linear transformation with rank T equals to find the nullity. Of course, if the rank is 2, the nullity is just probably going to be 2 in that case. So find the rank and nullity. You already know what to do with that. Just do the echelon thing. So this is 5 and 6 now. Let P3 be mapped to P to be defined by T of F equals F prime prime. Find the rank and nullity of F. Okay, so TF is F prime prime. So it means so F prime prime is definitely going to imply that you have, say, X. You have X. So, the other one, it was F prime. So you can use that correspondence to deal with this. So we have the kind of thing I just did here is what is happening here too. So you want to also try this out, determine whether it is on one to one or on to. Then let's a 4 by 5 matrix be with rank 3, find its nullity. Of course, if the rank is 3, the nullity is going to be 2 because we are talking, the focus is on the columns now. If the rank is 3, the nullity is 2 for sure because that's what's going to happen. Then problem 8, R5 to R4 be a linear transformation with nullity to find its rank. Okay, the rank should be 3 because you're focused on the R5 that it's coming from. Find all values of A for which the matrix A has nullity greater than 1. So if you want nullity greater than 1, of course, if it is 1, for instance, you have 1, 1, 2, and this will be 2, 2, 4, and this is 1, 1, 2. So in that case now, the nullity would have to be something like, the nullity would have to be, I mean, if A was 1, right? So you have this will be 1, 1, 2, this is also be 1, 1, 2, this will be 2, 2, 4. So the rank would just be 1, but we want nullity greater than 1. So for nullity greater, oh yeah, not I think that's even the answer. For nullity greater than 1, we need A to be 1. We need For nullity greater than 1, we need A to be 1 because if A is 1, the rank will be 1 and nullity will be 2. Yeah. So A is 1. It takes care of the nullity because in that case, 2, 2, 4 will be a multiple of 1, 1, 2. 1, 1, 2 is also the same thing as 1, 1, 2. So for nullity greater than 1, A is 1 easily. Then T4, P4 be defined by this. T of F is F prime. So this is exactly like what we did before, except that this is mapping P4 to P3. So you just want to go with that too. So yeah, this is the end of this. Thank you so much for listening. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed already, I must thank you very much for doing that. If you haven't subscribed, what are you waiting for? Go ahead and subscribe and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel by clicking on join, and that gives you some special privileges. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.